All right, let's go ahead and get started. My understanding is the notebooks are in the back, so you please collect your lab notebooks in the back. And then the draft reports are up here, alphabetized, so go ahead and pick that up. Let me go through first the calendar, and then I'll talk a little bit about the draft reports, and then we'll get into the technical content for this week. Okay, so we're in week number 11. And so the end is near. The end is near. Okay? We've got this week, 2 more weeks before Thanksgiving. We'll get Thanksgiving break. And then the week after Thanksgiving is the last week we'll be together. All right? So what's been done today is I've returned the graded drafts. And I'll talk a little bit about those and some suggestions for how you can improve. And so you've got all of this week and most of next week, and of course the weekend, to revise the experimentation reports. Okay, and they'll be due next Friday, not this Friday, but next Friday. So fortunately we have a bye week at football, so y'all have plenty of time to revise those reports. Okay, let me talk a little bit about the grades. Basically, there were 2 rubrics. You got 2 grades. One of them was on experimentation, and the other one is on writing. Okay, and so each of you should have a report that has a piece of paper pasted to the front of it. It's double-sided, so one side is the writing rubric, and the other side is the experimentation rubric. Now, what I did is the writing rubric has a maximum of 24 points. There's 6 different performance criteria, so 6 times 4 is 24. The experimentation rubric, I believe it has 4 criteria. Each one of them is worth 4 points, so it has a maximum of 16 points. So I sit there and I hover over the rubric chart, and I start off with a grade of 3, meaning most people make meets expectations. And then if the the writing looks irritating, my hand kind of drifts over toward needs some work or it's unsatisfactory. And if it's a really outstanding piece of work, then it goes over and you get a 4. Okay, so you can get a maximum of 24. Most people get some number less than 24. What I do then is I divide by 24 to normalize that grade, so you get a number between 0 and 1. Do the same thing with the experimentation grade. And so I divide by 16. And so that yields also a grade between 0 and 1. So then I add those 2 together. So this means you get a grade between 0 and 2. Okay, so these 2, the writing and the experimentation, are equally weighted, even though the rubric charts have different number of points. It's because they get normalized first, and then I get a number between 0 and 1 for each case. And so the maximum you can get here is 2. Now in Canvas, this shows up as a 10-point assignment. So then what I do is I multiply everything by 10. And so the result is you get a number between, multiply by 5. And so you get a number between 0 and 10. Get a number between 0 and 10. The class average on this was a 6.1. Okay, it's a 6.1. And the high was an 8. And the low, we won't talk about lows. All right? So there's a little bit of room for improvement here. Don't think that, well, if I made a 61, I've failed. This is just the way the grading is. It doesn't really matter what this number is. 61 is, you shouldn't look at this as a 61 and think that you've made a D minus or whatever. It's just a number out there. If you got a number under your name, take a look under your name. There's a number there, like 6.8, 7.1. You know, somebody out there got an 8. If your number is above the average, it means that you're probably a little bit better writer, or you wrote a better experimentation report than your peers. If your number is far below that, it just means the rest of the class may be a little bit better writer than you, or maybe did a better explanation of experimentation. Okay, so that's an explanation of how things were graded. Now, if I were to offer some suggestions and say what are some recommendations for improvement, I think the very first thing, number one, recommendations, the very first thing I would do is cut out the extraneous content. Okay. This is supposed to be a test report, an experimentation report, a report that validates whether or not something is working. And so a lot of students put in what I would call design explanations. They explained how the design worked, whether maybe it's how the keypad controller worked or how the drive worked. They went into equations saying this is how I calculated the resistor. That's irrelevant. Okay. Think of it for a moment that somebody comes to you and say, hey, I've designed something and it meets the specs that the boss wants. And your boss comes and says, hey, I want you to go and check it out. So you don't need to know the design details. So the design content needs to come out. What you need to do is to come up with a scheme to test the thing. And so focus on the testing. The other thing that is also extraneous are tests that are not relevant. Tests that are not relevant. As an example, let's suppose you're testing the keypad controller. What's important is to show that the keypad controller, or do a test to see how the keys are decoded. Right? There's 16 keys. And now the question is, when you do the test, what conclusion do you come up with? Compare it to the desired performance. The desired performance is you decode all 16 keys correctly. But some people said, well, let's also take a look and see how the speed of the motor goes. And they make a plot of motor speed versus buttons pressed. That's irrelevant. Okay, what you do with that information is irrelevant. Tests that are not relevant or data that's not relevant are things that need to be looked at. So basically, cut out the extraneous content. The second thing is there was a lot of vagueness about data that needs to be collected. This is the second section of the report. The first section should be an abstract saying, this is a report. We're going to report how we validated, say, the stopwatch. Well, what needs to be collected as far as data? There's a lot of vagueness. A lot of times people said, well, you need to collect data to ensure that the stopwatch is working. All right, that's good. But what do you need? What will validate that the things are operating correctly? So you would need something in more detail. So for example, you would say, well, this stopwatch has 2 digits. We need to collect the values of those digits and see if and do the experiment to see if they're sequencing properly. Maybe we need to collect the timing of the least significant bit. Okay, so you need to be a lot more specific. So be more specific in the detail that needs to be collected. The same vagueness kind of crept into the description of the experiment. The experiment description. Okay, so what is the procedure that needs to be done? Okay, so as an example, maybe somebody said, we're going to use the oscilloscope. We're going to use the oscilloscope to measure the voltages on the motor drive. All right? Specifically tell me how these things need to be collected or connected together. There's a lot of things, because we've been working in lab, they're very familiar to us. But you got to think for a moment, what happens if somebody steps in and they haven't been in lab for the last 11 weeks? And we're saying, go test this thing. Let's take the motor drive. You said, let's measure the collector voltage, let's measure the base voltage. But what is the input? That was left open, vague. Is it an AC signal? Is it a PWM signal? If it's a DC signal, is it high or is it low? You know what you're doing because you've been working on it for 10 weeks. We're entering the 11th week. But you need to think and sit in the shoes of the person who's been given the assignment to go test this thing. And so we need some more specificity, more specificness about the experiment description and the data. So I think those are the 3 main recommendations. Cut out extraneous content. It means for many of us, the report can be a lot shorter than what I have right now. Okay, I saw some reports that were 15, 20 pages long. It really doesn't need to be that way. Okay, this was supposed to be a very short assignment. So focus on what it is that you're trying to validate, and focus on that, and cut out the extraneous content and try to be a little bit more specific so that someone else who's not familiar with the work can reproduce the experiment. They don't have to reproduce the design. They don't need to know how to design it, because it's not a design report. All right, so those are the primary recommendations. So look over what I've scribbled on your report and what I've scribbled on the sheets, and work on it over the next 10 days to try to improve that report. All right, so we're in week 11 here. We're in week 11. And so what we're going to do this week, there's no new technical content. We may have to modify our C program a little bit in order to do what we call empirical modeling. The goal is by the end of the semester that we have a speed controller working. And one way to design the control system is to first have a model of what the process is, and then we may be able to use that model to design a control system. So today we want to do a little bit of, or this week, do a little bit of work in what I call empirical modeling. Then the next 2 weeks, there's no new content. I'll talk a little bit about the oral presentation that's going to come after Thanksgiving. I'll talk a little bit about how the controller might be designed and implemented next week. But basically for the next few weeks, we're trying to get a speed controller to work. We're trying to get all these things we've been working on for the last 10 weeks to try to get them all together to work. Maybe our keypad controller is still frustrating us. We got time to get that taken care of. Maybe our motor drive circuit is still getting hot. We need to maybe revise that a little bit. Maybe our A to D converter is giving flaky values, and we want to work on that a little bit. We have a little bit of time to get all caught up over the next few weeks and try to get the project to work. Okay, so ideally we'll try to get some data collected on our project, show that it's working just before Thanksgiving break. Then you can think over Thanksgiving break about how you want to do your presentation. And then the last week after Thanksgiving break, we'll do oral presentations in lab. We'll talk a little bit more about that next week. Okay, so today we're going to take a look at empirical modeling. And basically what we want to do is come up with a model for the plant. So we want to characterize the plant. I talked a little bit about the overall project. This is the project. It's in a block diagram form. This is the different hardware. We've got a motor that is connected to a tachometer. It produces a signal that we can use to determine the speed. You have two options right now. You can use measuring the pulse width of the AC signal. What is the period of that signal? The period is inversely proportional to speed, or you can measure the amplitude using the A to D converter. That information then passes to the computer system, which is also dealing with a keypad. It's not shown in here. The keypad is going to select a desired speed. Previously in lab, it selected a desired PWM duty cycle, but now we're going to change that and say it's going to be a desired speed. And so you can compare the actual speed with the desired speed, and then out here you're going to then produce a PWM signal with a calculated duty cycle. Rather than a duty cycle in a table, you're going to have to calculate that duty cycle and decide what will be the best duty cycle to apply to the amplifier. The amplifier runs off of 9 volts, and then which drives the motor. So what we want to do this week is basically come up with a model for all this stuff right there. So from the computer standpoint, it's getting information from a process, and it's going to send a command to the process, and hopefully everything is going to work properly. Okay, so the goals of the lab is basically to experimentally determine the control system model. Okay, so we are not going to do it analytically. We're going to do it experimentally or empirically. And this model may be used, time permitting, it may be used, it's not required. It may be used if you want to design a speed controller. So I'll talk a little bit about how that might be done next week. Those of you who are in 3500 control systems class, this is already familiar to you. You've been designing controllers already. Okay, so here is the block diagram of the control system. This is now modeled using the frequency domain notations, in particular the Laplace transform notations. Let me start over here with a motor and work around in both directions. We have an amplifier which is driving the motor. This is the motor drive, the single switch transistor. The motor is turning, and then the signal from the tachometer is being conditioned. This may be the comparator, which gives a square wave output, which we then measure the period, or maybe this is the envelope detector, which gives us the amplitude, and then we measure the amplitude with an A to D converter. Either way, we get some sort of signal right here, which is essentially the tachometer signal plus one of these two circuits. We're either going to be measuring period or the amplitude. All right, so we can treat all this as if it was the plant. This is all the stuff outside of the microcontroller. Within the microcontroller, we have this dotted box over here. And so what the microcontroller is going to do is it's going to determine what is the desired position. We call that the set point or the reference behavior. And that's going to be selected by a keypad action. So the user is going to mash a button on the keypad, and that selects the desired speed. Now, you're going to compare that speed. This is now going to be in bits. This information is also in bits. So we're going to compare those. And then we're going to get the error is going to also be in bits. And then we got to come up with some sort of scheme over the next few weeks to decide what should be the duty cycle. This is going to be for the PWM signal. And we adjust the PWM duty cycle by adjusting the capture control register, which is also in bits. Okay, as we adjust the capture control register, the duty cycle will change. And so this is the duty cycle that is the control to the plant. What we want to do today is we want to get a model for these blocks right here. Just one big block that is composed of a bunch of smaller blocks. Now I can redraw that thing and say it looks a little bit more like this. All the motor and all the electronics, all the signal condition is now into one box that I call the plant. The input to the plant is the control action, is the duty cycle, and the output is either the period or the amplitude, again measured in bits. And then in computer software, we're going to, this is now the microcontroller, it's got to do all these functions. The set point is essentially picked by the keypad, and then we make a decision in software how much error there is, and we'll come up with some sort of algorithm to adjust the duty cycle. But our focus today is on this box right here, the gold colored box. We want to come up with a model for just this thing. So what goes into the plant? Well, there could be amplifier dynamics, because that includes the amplifier. The electrical dynamics of the motor, because the motor has resistance and it also has inductance, so it's at least a first order model there. We looked at that model a few weeks ago. This is also a mechanical system, and so the rotor has inertia. The motor cannot change speed instantly, so when we change the duty cycle on the input, the amplifier drives the input to the motor, and the motor gradually speeds up or slows down. So there's a little bit of a time constant there due to the inertia and the inherent friction. The sensor itself also may introduce additional delay because you have to process that tachometer signal. Like, for example, if you're using the envelope detector, you've got an RC circuit there, and that's going to introduce another time constant. So there's a time constant here, a time constant here, a time constant here, maybe a time constant also associated with the amplifier. So this is overall a third or fourth order system. We could sit back and write all kinds of equations for each of these things, and that would be an analytical approach to modeling. Analytical approach. But we're not going to use an analytical approach because many times in life we don't know enough necessarily to write equations for all these things. What we can do is basically apply an input to the plant, measure something at the output, and try to fit a model to the observed data. So this is what is known by an empirical modeling approach. Okay, I casually joked in 3500 class, this is what we do when we men try to date women. We don't write differential equations describing their behavior, apply Laplace transforms and try to get the inverse transform. It just doesn't work that way. What we do is we do something. We do an experiment. We bring her flowers. We bring her candy. We observe the response of her. Or if you're a girl, you you see how that guy's responding. And then we form in our own mind some sort of a model of that person's behavior and how we should maybe approach that. It's an empirical, an experimental way of doing things. Now, what we're going to do this week is we're going to basically apply a step input to the plant. We're going to change the duty cycle from one value to another. It changes the duty cycle. It causes things to speed up. And then we're going to measure the response. And then given this input and this output, we're going to just try to fit a model to things. Now, most of the time in life, we don't know what is the real order of the system. I said for this thing, if we were to do things analytically, this thing's probably at least third order or higher. But when you just look at input-output data, you don't always know. And so a lot of times what we'll try to do is we'll try to fit the simplest model that we can to the problem. All right. So one way to do this, this is a diagram that kind of explains what we're doing. We're going to wait until a certain time, and then we're going to change the input. Let's call the input X. We're going to step change on the input, and then maybe the system responds like this. Maybe this is the speed. This is the A to D reading in bits. Okay, so initially it's at one value, not necessarily 0. It may be cruising along at whatever button 3 says, and then you say, let's do a change to button 6, and then it does this. So you do a step change in the duty cycle. The plant input is the change in the duty cycle, and then the system responds like this. Okay. So what we want to do is we want to fit a model to that we think would produce similar type of data. And so that's called an empirical approach to modeling. So we look at that model and we say maybe we could fit a first order model to it. And if we take a look at a first order model, it would have a differential equation that looks something like this. It says that the output is proportional to the input, and it is also affected by the rate of response. And so maybe we get a first order differential equation that looks like this. And if we solve this differential equation using ordinary differential equations, which we've taken back in our sophomore year, this is what we would get. Or we could analyze this using the Laplace transform, find the relationship between output and input, and we get a first order model that looks like this. We have two parameters, k and tau. So those of you who are have been in 3500, we're familiar with this idea. The idea is that maybe this first order model can yield data that's similar to what we have done experimentally. We put a step input right here, and when the response of the system looks something like this. And we just had to figure out a k and a tau so that this kind of fits our measured data. Okay, how can we determine these things? Well, one way to determine the gain k is we wait for the transient to settle out. We wait for the response to die out and settle down to its final values, and we compare the ratio of the change in output to the change in input. Okay, so we measure the output after a large time. Things are settled out, and we see how much the output has changed, and we divide it by how much we changed the input by. The time constant requires us to take a look at the transient period, the early part of the response. And one way we could do that is to know that for a first order response, the response satisfies this exponential response, and we could say we can estimate the time constant by seeing how long does it take to get to 63.2% of the final value. Okay, so graphically that's explained this way. To find k, what I do is I wait for the system response to settle out. I don't care what the transient is. I wait for the response to settle out. I look at how much I changed the input by, and k, the gain, is going to be the ratio between output over input. Okay, so I wait for large time. The time constant, there's several ways to do this. I could say that, let me say that the time constant is the amount of time it takes for the response to get within 63% of the final value. So I measure the final value, I figure out what 63% of the final value is, and I see how much time it took to get there. Okay, we remember e to the minus 1 is 63%. Okay, e to the minus t over tau, when tau is equal to when t is equal to tau, that's e to the minus 1, so we get this. So this is kind of a brief review of things that we saw before, maybe even in sophomore year circuits, when we were looking at the response of, say, an RC system and its time constant, or an RL system and its time constant. Those of us who are in control systems know that the time constant is also related to the settling time. So what we could do is we could study the transient, see how long it takes for the response to kind of get close within 2% of the final value. Say we're close enough, we've settled out, we'll call that the settling time, and the settling time is then 4 times the time constant. So that's another way to get the time constant. So measure the time settling time and then divide by 4. Or if we're, there's a word, I can't remember what the word is, you may wait 5 time constant, wait a little bit longer, get within 1%, okay. The information that you're going to get, your measurements, however, is going to be kind of noisy. It might be doing some of this, so you got to do some engineering eyeballing and figure out when have I gotten close, and then decide what your time constant is. Okay, so then what we could do is, now that we've got K and tau, we could enter it into a model in MATLAB. This is using the Simulink graphical user interface, but you could also use the transfer function model in MATLAB, and just say the transfer function has got a gain K, it's got a time constant tau, and it goes something like that, and then I could do a step response of that model. And we would look at that and then compare it to our data, see if it fits well. Maybe we have to go back and adjust K and tau. Now, later on, what we could do, and I'll talk about this a little bit more next week, is we've got this model now for our plant. We could construct a model for the control system and then maybe come up with some sort of control algorithm. One of the popular control algorithms in practice, in industry, is to use a PID controller. Historically, over the last 10 years that we taught this course, very few students will do this because it's kind of time consuming. So it takes a little bit of time to do that. But usually in a typical class, maybe we'll have 1 or 2 teams give this a shot. But there's a lot of other algorithms that could be used here, some heuristic control that you could design to make the system respond. And the goal of the project is to get a response, first of all, that settles out to the desired value. And if you take a look at these two, it's kind of a little bit difficult in this screen. You see this response is a little bit faster responding than this one. And that would be ideal as well, but it's not necessary. Okay. Let me talk a little bit briefly about some other types of responses that are common in practice. The human response is first order with delay. Okay, this is a typical response to excitation, is first order with delay. It takes a moment for the synapses in our nervous system to drive those muscles. There's a little bit of delay here, and that delay is affected by alcohol. And then this is our natural response. Okay, so this is one type of response. That model looks very similar to a first order, but it's got a delay factor. It's got this transcendental function, e to the minus delta t. Delta t is the time delay. Okay. This is also very common in describing a building like this. If we take a look at the time, at the response of, say, a temperature change. Okay, we've just gone through from summer to fall. We're now in a heating mode, and so it took time to get this system turned over from cooling mode to heating mode. And there's a delay here from the time something is activated on that thermostat over the wall to the time something happens over in the control room, the noisy rooms next to the elevator. And that delay is due to the fact that this building uses pneumatic controls. There's a plastic pipe that runs from that thermostat all the way over to the control room, where there are these big pneumatic actuators that open and close doors and adjust the amount of fresh air coming in through, or conditioned air coming in through the ceiling vents there. And it takes time for a pressure change here to propagate down that plastic tube, get into the control room, and finally that actuator starts moving like this. Okay, so you get this first order delay, first order response with delay. Also, say if you want to model the overall model of a paper mill. Okay, pulp comes into, not pulp, wood chips come into one side of the factory, and about half a mile down on the other end, we get newsprint, big rolls of paper. Well, somebody says, hey, the newsprint's not thick enough or something, or it's not white enough. We need to change something. You need to change the amount of wood chips going in. Well, the difference between where the wood chips come in and where the paper comes out is a long distance, a big old long conveyor belt. So by the time the new chips come in and finally show up in the product at the end, there's a long delay there. Okay, so it's very common to have first order response with delay. That delay is a huge destabilizing factor in a control system, as we have witnessed before when we watch our buddies get drunk. Their strength hasn't changed, but this delay compromises their ability to do things well. Other responses are second order responses. You will probably see this type of behavior in your experiment. You're more than likely going to see probably one of these responses this week. The difference between a second order response and a first order response is the first order response immediately takes off like so, and then settles out. With a second order response, it gradually gets going and then takes off. It could be underdamped, it could be critically damped, which is the fastest response you can get without overshoot, or more interestingly, it may be underdamped. It may overshoot, then undershoot, and so forth. Of these three models, the only one that's easy to do, the most straightforward one to fit a model to, is the second order model. And so it would have a second order form like this. It would have three parameters, a gain, a damping factor, and undamped natural frequency. This is just kind of review for those of us who are in the control systems class, so I won't go into it for too long. Second order systems have two poles. If they're underdamped, they could be complex, so I have both a real part and an imaginary part. They're functions of the damping factor and the undamped natural frequency. The time constant, how quickly the system responds. How quickly the system responds is a function of two of the parameters. It's a little bit more complicated. We just got more parameters to deal with. But we can still do an experiment. We can put in a step input, measure the response, and then try to fit some of the parameters. K is calculated identically the same way. Wait for the transit to settle out. Take a look at the difference in output divided by the difference in input, and that will be our gain K. The time constant is figured out in the same way. The time constant, tau, is the settling time divided by 4. All right, but now the time constant happens to be a function of these two Greek letters, zeta, the damping factor, and omega n. So I have one equation and two unknowns, but we can find an equation for the other unknown by maybe looking at this oscillation frequency. This oscillation frequency is a function also of these two, and so we could have two equations and two unknowns. This is equal to omega n times the square root of 1 minus zeta squared. Two equations and two unknowns. So conceptually not too difficult to do, but it would require a little bit more work. And so this is just kind of summarizing some of those ideas. The critically damped case and the overdamped case are much more difficult to do. I won't talk about how you would find those because the responses are very gradual and they're kind of uninteresting. You can get the gain, but to figure out the time constants is a little bit challenging. And so I won't delve into detail about that. If you want to know more detail about it, I'll be happy to talk to you about how we could do it outside of class. So let's talk about the lab procedure. Again, there's no new material really. There is a little bit of change in the C program. Okay. So first of all, verify that your hardware and your software is working from previous labs. We would like to be able to change the duty cycle, so make sure you have the ability to change duty cycle. Make sure you're generating a PWM signal. Make sure your motor drive is working. Basically see that the motor is turning. And make sure that you have some way to measure the tachometer signal and get an idea of how fast the motor is turning, either by measuring the period or by measuring the amplitude using the A to D converter. So you verify that everything is still working. Now, modify your software a little bit. So what you want to do is you want to measure the period of the tachometer signal, or you want to measure the amplitude. Once you've got that measurement, store it. Okay, store it in memory somewhere. Then a split second later, you're going to read it again, and then you're going to store that new value in a different place in memory. So basically make a big old table of all the different measurements. All right. Store all the values in an array. And then that array, then all the data can be transferred to the host PC after you have finished the work. All right. Then when you've got the data, plot it. Use some sort of tool, Excel, MATLAB, whatever, and then choose a model. Students for 10 years have been doing satisfactorily with a first order model, even though we know that the order of the model is probably higher than first order. Try to estimate your model parameters and write a transfer function, and then see how your model compares to the experimentally measured response. Now, I don't have a slide to show you here, but this idea of transferring the data to the host, there's some instructions. I'll double check tonight, make sure that the instructions are on Canvas. Okay, there's a lot of different ways that you can get the data basically from the debugger into a file that you can use to plot. Okay, I encourage you to also take a look at the page, the Canvas page. Look at the lab procedure on Canvas. This is the slides, but if you take a look at the lab procedure on Canvas, there are also some more details about this. But there's some instructions about how to do this. I'll make sure that it's there before I head out tonight. Okay, are there any questions about what we're going to try to do this week? No questions? All right, seeing none, that we'll go ahead. We're done today. We're dismissed. Those of you who just stepped in, be sure you pick up your report, and you'll have a good week.